So we have now this, there we go. We have now this domain that's been discretized. We need to then do like an energy balance on the node. Let me just kind of clean up what I mean in terms of discretization. So we've kind of done this already, but I'll just write it out real quick. So we have M, let's see. We have M nodes in X. We have N nodes in Y. So the total number of nodes, obviously, is M times N. M times N. So that becomes maybe, I don't know, interesting or problematic. Ease, it turns out, can only handle like 10,000 equations. So let's say you wanted to do 100 by 100 mesh, which isn't really that much, that many nodes. Ease is going to struggle to do that, okay? So we kind of have to pick certain problems for the sake of ease that are maybe a little bit more compact. When you really want to solve beefy problems, that's when you go to like MATLAB or codes that are actually dedicated for this kind of thing. All right, so this is the discretization. Let's write out the steps. So we have delta x, our x step is L over m minus 1. Delta y is L over n minus 1. I need to maybe clarify that, not L. Let's call that something else. What did we call it? H. Sorry, H over n minus 1. And then the x and y positions would be like xi is equal to I minus 1 times delta x. Yj is equal to j minus 1 times delta y. And then that would be for each of the I or j in their range, respectively. The other thing let's just kind of clean up now is this function, right? So we have some conductivity. So how am I going to implement conductivity for this problem? We had the two different domains. If x is less than a certain value, it's one conductivity. Otherwise, it's another. So in ease, what we would just do is say, I'm going to have some function. And function is going to take the position x as an argument. I'm going to have a conditional, which you can do in functions in ease. So I'm going to say if x is less than or equal to L underscore A, I guess that's what I called that first part, then we'll assign k for the ith node to be equal to, what was it, 0.035. Else, it's going to be ki is equal to 0.5, and then end if, and then end function. Right, so this in ease would allow me to just change the conductivity based on position. And that's all I have to do. Then I can just use ki in my equation wherever I want, and it gives me the relevant value. Okay, so not going quite as fast as I hope, but I think we'll get through enough of this by Wednesday that we'll have a shot at it. Okay, so let's go through the energy balance. We already did I think we can do this, and then I'll kind of wrap up. Let's go through an energy balance. What I want to do first is look at a constant conductivity. I want to look at a constant conductivity case. So what this means is I'm temporarily suspending this conductivity as a function of position. I just want to do it the kind of regular way. You'll see what that looks like, and then later, probably next time, we'll go back and do it the way that's specific for this example, because you'll see some important differences. So we had gone through this. I'll just kind of hit the highlights. We have the heat flows going in each direction. So this was top, left, right, and bottom. So I'm going to add up all the heat flows that are related to this. We're doing the energy balance now. And that looks like this. So Q dot Rij plus Q dot Lij plus Q dot Tij plus Q dot Bij is equal to 0. All right, that's just adding up all those terms. We have to note what this is valid for. So this is for an internal node. Right, so we're saying this is for all. Remember our symbol for all I in the set of 2 to m minus 1, and for j in the set 2 to n minus 1. So we're short a number of equations here, right? We're short not only in each direction independently, but the combination. So the entire square around the perimeter of this domain is not defined by this, right? The boundaries are not defined by this, which is what we want. Let's go through and write out the rate equations here. This is kind of the last interesting thing. So let's see. Q dot, let's start with Q dot R, ij. So what is the heat transfer from the right from, what is this node? So this one's here, it's ij, this is I plus 1 j. So from the right, Q dot R is going to be the conductivity K. Again, let's just assume that we have a constant conductivity right now. And then we need to look at what is it? The resistance is the distance to conduct over the cross-sectional area times AC. So K times AC is going to give us, what do we have here? K times AC, W times the, sorry, stumbling over my words here. So I'm looking for the area of this guy here. All right, so W into the page, and that's dy, delta y, delta y. The distance to conduct is from this node to this node, which is delta x, right? Delta x. The temperature potential is from the direction we drew it is T I plus 1 j minus T I j. Okay. So that's Q dot from the right. The really important thing here is distance to conduct is the delta x. It's always delta x. The area that's available is W times delta y. So you're always looking at like you have to be careful about that area, be careful about that distance. Let's look at Q dot left. That's basically the same. Q dot L I j equals K W delta y over delta x T I minus 1 j minus T I j. Then let's look at the one from the top, and then we'll leave it there. So from the top, we have K times W times what's the area from the top, right? That's going to be delta x times W. So W delta x. Distance to conduct is delta y. Now we have T I j plus 1 minus T I j. Q dot bottom is basically the same thing, right? Just from the other direction. All right, so now we have these four rate equations. We plug them into that energy balance above, and we have our first nodes. Yeah, one question before we're done.
So what happens to the negative sign that's usually in front of the K?
Yeah, really good question. What happens to the negative sign? The negative sign doesn't appear because we're using a resistance model, right? We're saying high temperature to low temperature is the direction of heat flow. The distance is where that normally comes from, right? We're saying like x0 minus x1, which gives a negative. Here, because we're using resistance, we just omit the negative. Okay? All right, thanks everyone. See you Wednesday.